what we're going to be going over here, eigenvectors and eigenvalues, and we're going to get a basic understanding of what these are. So when you're looking at eigenvectors and values here, you're going to have to be looking at it in terms of some function here. And I've just got a multivariate type calculus function here, and it's really the production function here. So what we're going to be looking at, just move over here. Okay, so this is our function here, and what we're going to be following is some gradient path. This is a path here of our maximum output for our function based on, in this case, it's material and labor here that we're dealing with here. But what we're going to be looking at the eigenvectors and values at a specific point here. Okay, so let's go and let's look at what we have. So when you're talking about eigenvectors and eigenvalues, you have to have a square matrix. In this case, it's a 3×3 square matrix that we have here. And the matrix is based on the second partial derivatives of our function here. Okay, so what we would do here, again, based on, we got to have some solution point here. So based on some cost constraint here, I solve this 3×3 matrix here, and we have a solution point here. Those are the specific points. 7.8 here for labor, which I can just say is my y value here, and m here for material is my x value, 6.9 units here. So we've got a solution point here. We put it into our matrix here, and then we come up with the matrix based on that solution point here. And then we can take that matrix that we have here, there's just a block of numbers here, and we can solve that matrix here, and we come up with, based on the determinant here, and we're going to have some determinant value that we have here. And you can remember this determinant value because it's going to play a role here when we look at our eigenvectors and eigenvalues here. So what we would do here, when we're dealing with the eigenvectors and eigenvalues, we have to take this determinant matrix, or this block of numbers here, and we have to set it into an identity matrix here. So we take that A matrix here, 3×3 matrix, and then we would subtract from it here an identity matrix, and that's really, this is the eigenvalues, that's these lambda amounts here, and this is the identity matrix. You can see it's got a diagonal 3×3 matrix with a diagonal here with the lambdas, or the eigenvalues here put into that matrix. So you would subtract that from our determinant matrix here, and you're going to come up with the matrix here with the eigenvalues included here. They're subtracting it from this, our A matrix here, and then we come up with this matrix. So you can see what's going on here. We included those eigenvalues here, well, the lambda, which represents our eigenvalues. Now we have it in the matrix here, and now we can go ahead and solve for those eigenvalues here. So you just set this matrix here with your identity matrix with the eigenvalues in here, set it equal to 0, and then you can solve for it. You're going to come up with some characteristic equation that we're showing here, and you can see it, this lambda is raised to some exponential amounts here. So what you would do here, and you can just factor those out, you're going to come up with some lambda factored amounts here, and then just solve for it, and this is our eigenvalues here. Again, we've got 3 values here that I'm showing here. Now just remember, I went through this here just to understand where these numbers come from, and you really need some computer software system to solve a matrix like this when you're dealing with these multivariate calculus problems, and when you're looking at a larger matrix or a 3×3 matrix. Okay, so that's where we got our numbers from. So now let's go and let's get into those eigenvalues and eigenvectors. Okay, so what we've done here, what I'm doing here, I'm not going through how we go about getting the eigenvalues and eigenvectors. I'm just putting them into a MapleSoft, that's my computer software program here, and it gave me and we looked at the basics and how you got your eigenvalues here. That lambda amount, we have 3 of them shown here. But then we would do the same thing for eigenvectors here using our computer software package here, and we're going to come up with a unit vector that's less than 1 that we're looking at. So what we're dealing with, we x, y, z coordinates here. So for each of these eigenvalues that we have here, for example, this first one, a 395.521, this is the x, y, z unit vector for it, and we're going to get into that and how we can manipulate this unit vector into the eigenvalues here. So you can see it's got x, y, and z, all in less than units of 1 here. And you'd have the same for the other 2 eigenvalues that you have. Each one has a unit vector here, x, y, and z coordinates. Okay, so what we're going to do here, and what we're talking about when we're dealing with these eigenvectors and values, just understand what we're doing here. We take that unit vector here, or here's our determinant matrix here, and this is before we included those lambdas here. That's the determinant matrix based on our solution point here. We take that determinant matrix A here times the dot product here of our first, let's just say our eigenvectors here based on this first eigenvalue here, those unit vectors. Take that times our determinant matrix here, and that's going to give us the x, y, z coordinates here for our eigenvalue here at 395.52. Okay, so that's just the math or the arithmetic that we're using here. So what we're doing here is we're just taking that determinant matrix here, taking the dot product with our eigenvectors. Here's our eigenvectors, here's our determinant matrix, and that's going to give, that equals our eigenvalues here. And those eigenvalues are the coordinates x, y, z here based on that eigenvalue here of 395.52. Okay, so what we're doing here, really, what we're doing here, it's really, we're answering this question: what happens when you multiply a vector by a square matrix? So we had the square matrix shown here, our A matrix. Here's our unit vector here. So what you're going to do here, you're going to get another vector of the same size, which we did, showing up here, the same size. You can see it. This is our eigenvalue vector here. We had the unit vector here. Here's our matrix. We dot product those, and this gave us our eigenvalues here. Okay, so what you did, again, we got the vector here the same size. Typically, both length and direction of this matrix vector product will be different from the original vector. What we're really saying is we have a special case here. When you're dealing with these eigenvectors and eigenvalues, you have a special case here. That's where the vectors have the same direction when it's equivalent, and it's equivalent taking these vectors of same direction. We're talking about the matrix and this vector here have the same direction that we're looking at. We'll look at that. Then you just take, they're just equivalent here by multiplying the vector by a scalar amount. So that's what we've done here. We've taken our matrix here a unit vector, and then we've come up with our eigenvalues here. So we scaled it, we just scaled up our unit vectors here by our determinant matrix to get our eigenvalues here. Okay, right, we did. So this, okay, what really this does here, it leads to some of the most important applications in linear algebra. So in order that we have eigenvectors and eigenvalues, we'll get back to our point here. They all have to be, that's production function, or this function that we're analyzing. It has a direction here. You can see my little, I've shown them here in a whole bunch of arrows here. These are really the gradient or the increase here, the greatest increase here in our function for our output here. And in order for these eigenvectors and eigenvalues to work, both the vector that we're dealing with and that function that we deal with have to be going in the same direction. All right, so you can see what's going on here. This is my gradient path, and this is what we're following up here for our eigenvalues. And we're going to eigenvalues and eigenvectors, so they are going in the same direction that we're dealing with. So you got to have some matrix going in the same direction, and we have that here. And the cases here where I know that I'm going to come up, I got a system here. I'm going to develop a system along here, come up with really some new coordinate system, generally what you're looking at when you're talking about eigenvectors and eigenvalues, based on that function that we're looking at here. In this case, we're maximizing this function. Okay, so let's go and we'll continue on now, just looking at how we set up, look at these eigenvectors here pictorially. Now let's get a pictorial understanding here of these eigenvectors and these eigenvalues here. So we'll start with our eigenvectors, which really are the unit vectors. And what you're looking for here is those vectors that we calculated here, and they'd be between a -1 and a +1 here. Now they could be really any length here, but you like to deal with that unit length. Okay, so what we had here previously calculated, we had those three vectors here that I'm showing, the blue one, the red one, and the green one. And to get an understanding of what we have here, based on our previous calculations, I plotted these out here in the x, y, z coordinates. Now, what we're going to find out here is with these eigenvectors, we really, they like to change to a new coordinate basis here, but we'll just leave it as it is here with our x, y, z coordinates, but to understand that. Okay, so what we have here, the blue one and the red one here, they form eigenplane. And that's really its tangent to, in this case, the level curve or our production function that we looked at here. So let's go down and look at that. So that tangent plane, or that eigenplane here, would be tangent to, and I'm really looking at the first point that we have here. So this is why we have the tangent plane. And again, the red vector and the blue vector make up this eigenplane here. But the one that's we're really looking at here is this green vector here. Now that's the one that's going to be on the gradient here, and that's that line that we're looking at here for our maximum output based on our production function. And really that's perpendicular to the level curve here. It could be either minus or plus here, but it has to be perpendicular to it here. And when we're talking about these eigenvectors, they always start out with the xyz coordinate would be the 0, 0, or 0. So that's really our first vector here. Okay, so let's get a little better understanding of our eigenvectors here, just going over and looking at it in this way. So what you have here, really, they're talking about a new coordinate system here. But let's just say it's lying in our xyz plane here. But what is important here, it's called the eigenspace, and really those are our coordinates that we're dealing with here. And really what we want to point out here is our eigenplane here, made up of the red vector and the blue vector. Again, those are unit vectors between -1 in this case and no less than -1 and no greater than +1 here. Again, our 0, 0 vector, our starting point here. But the point is here, this green one here, that has to be 90 degrees, or it is 90 degrees here, perpendicular to our red vector, our blue vector, and our eigenplane. So this is really, we're talking about a vector direction here when we talk about this eigenspace here. But really what we're dealing with here is these three vectors. When we start multiplying these eigenvectors times our eigenvalues here, and what we have to do is we're sliding up and down, either shrinking or either increasing or decreasing our eigenvalue here based on where we make our selection along each of these vector planes. Now, along the vectors. So you're going to move up and down here along your red vector. Same with your blue vector. You want to move up and down here. You can move in a negative direction as well. I'm not showing it here. But you're going to be moving some scalar amount here on those unit vectors. And the same with your green vector. You're going to be moving up and down here in some scalar amount. Okay, so that's our eigenspace here. And it's really the vector direction. Okay, so we've got our plane here. We got our three vectors. You understand what's going on there. And we're talking about, we're not going to convert it over here, but they do some conversions here. Really, you come up with a new coordinate basis based on your x, in this case, our three-dimensional, our 3D XYZ axis here. Okay, so that's our unit vectors. Now, when we apply these unit vectors here, these eigenvectors to, and let's move up here and look at that here. And wait, maybe better go down here, and before we go on, let's just make a point here about this eigenplane here. Just a note, we would take this eigenplane here with those our three vectors, and we'd overlay it at whatever point we're looking at, in this case along that gradient path. And I got the level curve shown here in our function. Our level curves, those are those red lines here. And just make a point of it. We'd take this eigenplane, it would be tangent to some point at the particular point that we're looking at here based on our production or our function here. And then again, this green one here, that would be perpendicular to whatever point we select here based on our level curves. Okay, so just understand that. Okay, so now let's go up and let's look at our eigenvalues here. Really, that is the axis length. So we got, this is the case here where those eigenvalues, they're scaled up or down based on those eigenvectors here. Okay, so what we're doing here is we'll look at all three of them here. We get, again, I laid this out in the XYZ coordinates, and actually they really share the same coordinates except for whatever scalar amount we have here. They share the same coordinates as our eigenvectors do here. The direction remains unchanged, your X, Y, and Z axis for three of those vectors that we're looking at here. Okay, so in this case, I've got the three vectors here. I got this yellow one here would relate to the blue vector here. and that's over this side, sitting on our eigenplane, or our eigenplane here. And then this yellow vector, also sitting on the eigenplane, would relate to our red vector down here. And then this green vector here, I actually am showing it going in a positive direction, but if you look at the scaling here, you'll see it's actually negative. I got it inverted here, but this green one relates to this red vector here. And again, that's the shortest vector, and really that's the one that you want to be looking at here when you're talking about determining these eigenvalues and understanding what's going on here in this case of the determinant, or the change here in value or volume that we're looking at. Okay, so that's what we have here. Red one, that red short one here, relates to this green vector here, and then the two yellow ones go with the red and blue over here. Direction remains unchanged. Same direction as we have with our unit vectors. The only thing we're doing is we're scaling, taking those unit vectors times some amount, and we're scaling them up or down here along these vectors, or these vectors. It's really the axis length. Now remember, they could go in a negative direction as well here. So what we're doing here is we're taking that matrix here times whatever vector, it's a dot product, times our eigenvector, and that equals our eigenvalue here. That whatever eigenvalue we have here that we calculated times that vector. So the unit vector is involved on both sides of the equation here. Your matrix times your unit eigenvector equals your eigenvalue times your eigenvector, and we'll look at those calculations. Okay, so I guess we've talked about made our relationship here between our eigenvalues, which is really the axis length here, and our eigenvectors, which is the unit vectors, or the unit length times whatever eigenvalue we have here. Just understand that there is that relationship. This plane, they're sitting on the same plane. It's only a scalar amount between the two. And we can scale it up or scale it down depending on the situation. We're looking at a specific point here, so we're going to have specific values here. Okay, so I guess we've talked about that. Let's go over here and let's just look at the calculations here. Okay, so again, looking at our unit vectors here, I got it kind of tilted here, but nonetheless, you got that 90 degrees. The green one here is 90 degrees between our red and our blue here. And again, this is a 0, 0, 0 point here. Okay, so let's look at this first blue one here just to understand what we're talking about when we make our calculations. This involves the numbers. Okay, so we have, for this blue one here, we have a related eigenvector here, that minus 700. This is the x, y, z coordinates that was calculated with the software. So we got the minus 0.7, 0.328, and 0.635. See, all less than 1 and all greater than minus 1 here. We had a minus and some pluses here. So you're going to end up with minuses and pluses, but I've got the unit lengths here either not less than minus 1, not greater than plus 1. Okay, so to determine our eigenvalues, really have understanding the eigenvalues where they have laid out in the x, y, z coordinates. You have really two different ways to calculate these eigen terms here. So taking those, let's look at this again. This is the blue one here, that blue vector on our plane here. That's the one we look at. Here's our unit vector. You can either take the diagonal matrix of the eigenvalues here. In this case, it was a minus 411.46. It's a diagonal, a 3 by 3 matrix here. You see the zeros. The diagonal is that eigenvalue here. Okay, so we've got that. You can see that, a 3 by 3 matrix times this vector. Or you could take the matrix itself. Remember that determinant matrix that we started with? It's again a 3 by 3 matrix times, and it's got the values for the determinant values for that exact point that we're looking at. You can use either one here. You can either determine your determine your coordinates either through the diagonal matrix here, which are eigenvalues, or the determinant matrix with all those values. Okay, so let's just go and let's look at that. So we would do a dot product here. When we're talking about it, you're just taking this diagonal matrix. Remember, dot product, it's not exactly times it, but the dot product of this diagonal matrix or our determinant matrix times this vector here, times that vector. And let's just go up and look at that. So that's our blue one here, our 3. Let's look at that. Okay, here it is. This is the vector here with our eigenvalue, or that scalar length here that we have. Now we knew what the scalar length was. It was that minus, that would put it in our diagonal, minus 411.460. But what we wanted to do is find those coordinate spaces here by taking our unit vector times the diagonal matrix dot product or the determinant matrix. We got up our unit vector, or we got our coordinates, our x, y, and z coordinates. In this case, 287.850 minus 135, you're going to end 0.0 here, something, and then minus 261.43. You're going to get a bunch of minuses or pluses here, depending on how you're looking at it. But nonetheless, what you've done here is you've taken A here represents that unit, or our matrix that we're talking about, times the unit vector, or dot product times unit vector, equals the lambda here, which is really the eigenvalue, or that accent length, times our unit vector. So that's the relationship. Okay, so let's just go down maybe and let's look, and just make a point here. The direction is the same as the eigenvectors. These directions we have here, all we're doing is we're taking, and we calculated the scalar amount, but we had to come up with the exact points here in the x, y, z coordinates. Okay, so let's just go down here and look at further here. Okay, so let's look at 1 here. That's that green vector here. That's the one where really our point of interest is here. These other two lie on our plane here, which is a tangent to that production function. But this green one is really a key to everything here, because that's really looking at our change here. Again, here we take, you can see here, I'm just using the diagonal matrix we had that was a minus 46 here, was for the eigenvalue for this green vector here, times the unit x, y, z coordinates, the unit vector for it. Okay. Or you could take the determinant matrix, the same thing here, but just leave it at the diagonal matrix here. Just understand what the diagonal matrix is. Okay, so if we do that, and then we'll look at that value up there. And then the second one here was that green one here that we talked about. Then the second one here was that red vector here. That's sitting on our eigenplane here, as we call it. Okay, again, just take the unit amount, x, y, z here, times, or the dot product times the eigenvalues. In this case, it was at 3.9520. Okay, diagonal matrix. Time it, that'll give us, and we can go up and look at it. Okay, so the first one here, that was at minus 46 here, and it was the x, y, z coordinates here. I'm showing it, 1.80 here, minus 40.2, and then plus 22.67. You can see it's actually pointing down here in a negative direction here, based on our eigenplane here. And really, if we looked at this vector here, this green one I went down here, that's really should be pointing down too. It's really in a negative direction as well here. Okay, and then this other one, our second one, again we had, I don't know, whatever that was, it's right here, 395, that was the eigenvalue here, and then these are the unit amounts here, 282, 145, and 235, representing the x, y, and z coordinates here. Okay, but you can see these are sitting on our eigenplane here. The only thing we've done here by taking those unit amounts is we come up with a scalar value here, which we knew we used in our we didn't have to have it. All we could have used is the determinant matrix if we didn't know those. But nonetheless, we use it either by diagonalizing it times dot product diagonalized times the unit vector to come up with the exact, or scalar vector, as I would call it here, the scalar amounts that give the position here of each of those vectors in space. And just remember, everything starts with 0 or 0, 0, 0 point. So the question is, really the one that's not sitting on this plane here, these are the longer vectors. You always look for the long vectors. They're going to usually be sitting on the plane that you established that's going to be tangent to whatever function you're looking at. The key is this short one that we're looking at. So that really becomes the determinant value, or the change that we're looking at. So that's the one that we really have in question, or the change here. Just look for the short ones here. Now, we did all our calculations here for our eigenvalues. That was the scalar length here. Let's just go up and let's look at the determinant. Remember, we calculated determinant based on those points here, and that was 7.528 10 to the 6th here, which is, so really that's just taking those eigenvalues that 395 here. You actually take the absolute value here, but I have some negative, the negatives cancel out. You take the 395 here, and then there would be some decimal point here. You take the 46 here, just take the absolute value, or you can use minus 46 in this case, and then you look at the 411 here. You can see the two long ones, 395 and minus 411. One's going to be minus, one's going to be plus. Okay, and then you got the 46. So if you take those values here times each other, those eigenvalues, 395 times minus 411, well, you take the absolute value of that, times 46. You're going to get the determinant here. So that's the key point here, the determinant here. 7,528,000, or 7.528 10 to the 6th. Okay, so that's really key here. So then just to sum it up here, these eigens really follow our gradient path, and I've just laid out, this is our gradient path, and we have those, we got, say, 3 different points here. So those eigenvalues, in this case, they follow the path here, our maximum output that we're looking at here. Okay, so that's pretty much the relationship here when we're talking about eigenvalues and unit vectors and so forth here. So those are just the basics. Just remember, what is key here is when you come up with those eigenvalues, in this case I got those 3 eigenvalues, just take the absolute value of each and multiply them times each other, and you're going to come up with the determinant value here. And remember, the determinant is really the change in volume, or the change that we're looking at here when we're moving along that gradient path. Okay, so I guess that pretty much summarizes our discussion.